We move on now in these lectures to talk about what's called WKB theory. It's yet another asymptotic or perturbation method that we can use, and it's available for us for certain types and classes of problems where the underlying assumptions and techniques of this make sense. So I'm going to walk through, we have 2 lectures on this, and walk through the basic theory and also talk about what WKB actually stands for. So WKB, it goes back to Wenzel-Kramers-Briand. Sometimes it's called WKBJ. You add Jeffreys onto there, but I'm just going to stick with WKB theory. And it's a very simple idea. It's basically an amplitude-phase decomposition. So what we're going to do is going to take our asymptotic approximation and put it in a very particular form. In particular, here's what it's going to look like. The solution U is going to have some amplitude times some exponential. And the idea here is that I want to discover A of x and S of x. So those are going to be the things that I'm going to do an expansion about. So I want to understand from a perturbation point of view, how does this amplitude A of x, I'm going to do a regular expansion of that, and this S of x evolve for the problem I'm considering. So S of x is also going to be expansion. And the parameter delta here is going to be a small parameter. So notice if epsilon is, or delta is small, then this means that this exponent is often very large. So in other words, you're dividing by something small, so this gets to be very big. So in other words, the phase information is carrying the leading order behavior of the problem. Oftentimes, WKB theory is used in the context of fast oscillations of a problem, where in other words this S of x is complex so that you get a very fast phase dynamics. And you're interested in that, but what you're really interested in is what's happening on slower scales from that. And so the WKB approximation, this amplitude phase decomposition, gives you a formal technique to do an expansion and to compute out different contributions to the physics. This is actually a very nice technique, and it's had a lot of mileage in optics and quantum mechanics. Those are the 2 dominant areas of application because they often have high-frequency oscillation phenomena involved in them. So I'm going to start off with an example, and here's going to be the example. I'm going to take a problem like this, epsilon squared uxx plus q of xu. So this is going to be a boundary value type problem. And I'm going to just show you how this kind of amplitude phase decomposition of the WKB theory works out. So the idea is the following. We're going to expand it here. Here's the expansion formally. U of x is e to the s of x over delta. I'm not even going to worry about the amplitude for a minute. I'm just going to simply take this thing and expand it. Notice what I'm going to do with s of x. I'm going to take this s of x and expand it in a Taylor series. Now what we're going to see is when we do this expansion, we're automatically going to pull out sort of, in some sense, contributions to the amplitude changes that we get in this problem. Okay, so that's the problem we're going to consider. We're going to take this here, plug it into there. Notice there's 2 small parameters now. There's this epsilon, which I'm assuming is a small parameter. So this is a singular perturbation problem. And I have this delta, which is another small parameter. Just like when we did boundary layer theory or initial layers, we're going to have to establish some kind of dominant balance physics. In other words, we're going to have to do a distinguishing limit between delta and epsilon in order for this to make sense. So let's go about this approximation. So I plug that in and start to collect powers. So first of all, here you go. Here's what we have here. I have to compute the derivatives, right? First, so I have uxx is equal to q of x. So first I'm going to compute the first derivative, compute the second derivative, and you can see I start getting this s of 0 and s1 and s2 all having derivatives in them. And I plug that in now to my governing equation, which is epsilon squared, second derivative, and here is the second derivative calculation I just made, is equal to q of x times u. And notice all the exponential terms drop out. So both sides have this contribution, e to this exponential on both sides, so they can cancel out. And so what you're left with, though, is here is what's the result of a second differentiation of the problem. And notice what pops out here. You have your s naught x divided by a delta squared. So again, delta is small, so you're dividing by something small squared. You get this term here divided by delta, some other terms just divided by delta, and so forth. And so you get an expansion in terms of delta. So let's collect the leading order term. The leading order term is going to actually be this here. So on the left, you say, I have this epsilon squared here, multiplying this. I have a delta squared here. And if I want to balance the leading order term here with the q of x, if I don't balance the q of x, then if, for instance, if the dominant balance here is something that goes to 0, then it means q of x has to be 0. But presumably, q of x is some order 1 function. That means the dominant term on the left side has to balance it. So the dominant term is the one here that's divided by delta squared. That's the biggest term. And that is going to balance that q of x. And so what we do is say, take that dominant term and say, OK, epsilon squared over delta squared is s naught squared over x. And you want this to be around order 1. And in order for this to be order 1, it means that delta is like epsilon. So we can just take delta equal to epsilon. And then this here ratio is just 1. So what we've just done here is found the distinguishing limit which will allow this problem to make sense. Otherwise, if delta is much bigger or much less than epsilon, then you can show through doing your distinguishing limits that in fact you get nonsensical results. So it's important that we do this dominant balance or distinguished limits up front. You don't know necessarily ahead of time what delta should be relative to epsilon, but once you plug it in and you do just some, essentially a sanity check on the kind of solutions, what you find is that in fact you get the scaling law that you need, and delta here has to be epsilon. So now once we have this, I can now do this expansion and come back to the expansion, put in that delta is equal to epsilon, and then this is what happens to the left-hand side. Now I have this s naught, the first contribution, x derivative squared, plus here's my epsilon contribution, plus some higher order terms, plus another epsilon contribution in higher order terms equals q of x. And now I do exactly what we do when we do perturbation theory, and we collect powers of epsilon terms. So here we go. At leading order, what I find is that the derivative squared of s naught is equal to q of x. This is what's called the Eikonal equation, and this is sort of comes out of optics. So Eikonal and transport equations are standard terms that come out of optics from the 60s, and in fact, these are sort of classic, important equations that tell us quite a bit about the physics of the system. At order epsilon, you get the transport equation, which is essentially some equation involving s naught, but now involving s1. So you can calculate for s naught here, s1 here, and then you go to higher orders. The first two of these have these names, Eikonal and transport equations. And oftentimes, it is enough that if you compute the Eikonal equation and the transport equation, it gives you a lot of critical information about the physics of your system. There are cases, of course, you're going to have to go to higher order to get something that at least is reasonable approximation to the problem. But oftentimes, you can do it just with those two contributions. OK, so let's go grab the leading order solution. There it is. So actually, the leading order problem is just this. So all you have to do is take the square root. So that gives you square root q of x on that side, and you have s naught x, and then just integrate once. So it's trivial kind of to solve. And here are your solutions, plus or minus square root of qx integrated across x. That's the solution to the Eikonal equation. So what s naught is, remember that we made an assumption about this amplitude phase. So you have e to the s naught over epsilon now. And this is the leading order contribution to this problem is given by here. Once you have that solution, you can now go to higher order. And the higher order equation is given by here. Here's the s1 equation. And now s naught is just the right-hand side here, which you can easily compute this now that you have the exact solution. And this thing here actually is just the log of the derivative of s naught and the derivative of that. So you can just integrate this once. And notice the reason I wrote it this way is because there's a dx here, which when I integrate it just comes out. And then what you end up with is minus a quarter log of q of x. So this is the transport solution, is this contribution right there, okay? The log of that q of x that you have. So I've got my first two corrections, and I can come back to my formal WKB approximation. And the formal WKB approximation is given right by here, right? It's u of x is equal to, there's the expansion, and then I just computed S0, I just computed S1. So I can put those in right here, and notice that the S1 has an epsilon in front of it, right? So that's going to cancel with the epsilon on the bottom. And then what you do is you have e to the this, e to the that. You can separate them, and you hear what you get. You have e to the 1 over epsilon, the square root q of x integrated, e to the minus epsilon over 4 log q of x. And notice the exponent and the log are going to be able to cancel each other out. And so what you end up with is exactly this solution here. Q of x to the minus 1/4 power, e to this thing here. Notice the epsilon parameter shows up here. So this is a very, so it's, you get this integral divided by epsilon, which is small. So this is a big contribution here. And notice that the amplitude change directly came out of that S1 contribution. So the transport equation gave me what the amplitude looks like, whereas the Eikonal equation told me exactly what's going on into the phase. This is a second order differential equation, so I expect two linearly independent solutions, and in fact I have them because remember I had this plus or minus square root q of x that I could have put in there. So I have two linearly independent solutions to work with. So this is fantastic. Just by doing this contribution I have an asymptotic approximation to what the solution looks like in this WKB framework. So what do I really have? Well, what I really have then is some arbitrary constant C1 times the solution with the plus sign in front of the QX plus C2, the solution times minus with the QX in there. So that's your generic solution. And of course, once we have boundaries values that we have to impose, that's going to determine what C1 and C2 are. At this point, we haven't talked about what the boundary conditions are. Mostly what I'm just showing you is how this expansion works. Once you put in the boundaries, that's going to determine C1, C2. So let's go and go even higher order. So in fact, you can just continue this perturbation expansion. And for that specific problem, here's your contributions. So you can just keep going to higher order. And these are not that hard to calculate because it's a fairly simple problem. We have the leading order contribution, S0. That's the Eikonal contribution. Here's your transport equation solution, which is just log of q of x. S of 2 is now a more complex integral that you could do. And notice S of 3 is actually, you can compute that exactly just like this. There's no integral in this. So in fact, all the even terms, or odd terms here, you see that you can undo the integral because there's this log contribution, whereas the even terms here, you're left with an integral representation. So once I give you a specific q of x, you could evaluate these. Okay, so that is the hierarchy that you would get from doing this expansion. Okay? And so now let's go back and talk about, let's maybe do a specific problem with a q of x. But before we do a specific problem of that sort, I do want to come back to a problem we've been considering, doing boundary layer theory, in which we do inner and outer expansions. So I want to come back to this classic problem we did when we were considering boundary layer theory, which is there's an epsilon in front of the highest derivative, b of x u of x, c of x u, plus some boundary conditions. Here they are. I live on the domain 0 to 1. On the left it's a, on the right it's b. So this is a singularly perturbed problem because I have the epsilon here in front of the highest derivative. So when epsilon goes to 0, right, then you have a first order differential equation, and it can only satisfy one boundary condition. And so I need to take into account the fact that as I get corrections, there's going to be a boundary layer formation somewhere. Now what we did previously with this is, if you look back at those lectures on boundary layer theory, what we had done is we said, let's look at the outer solution, and let's look at an inner solution. Where is a boundary layer likely to occur? Is it on the right or the left? Is it in an internal boundary layer? In fact, in those previous lectures, we showed the conditions on b of x which determine where that boundary layer will occur. Once we have that boundary layer, we do an inner expansion, and then we do matched asymptotics. We take the inner expansion as it moves to the region of the outer expansion. We take the outer expansion as it moves to the region of the inner expansion, and we match the solutions. And that's how we did these uniform solutions using matched asymptotics. And now what we're going to do is try to do a solution of this using this WKB approach. So let's go ahead and expand. Take my solution, u of x, assume it's in this form, e to the s of x over epsilon, where I've expanded s of x in terms of a regular perturbation expansion. Notice I'm already going to assume that the distinguished limit is epsilon. Now we already know that from boundary layer theory for this example here, and I'm also going to assume that b of x is positive in this case for the whole domain. Okay, so there's my expansion, my formal expansion. I'm going to take this expansion, put it into the governing equations, and let's see what we get. So when we put this in, we have to take the derivative and the second derivative. So it's a little bit of work, but at the end of the day, here's what you get. Epsilon squared times all these terms plus b of x, these terms, plus c of x. The exponents all cancel out, and so what I'm left with is now a perturbation expansion that I have to collect like powers that exist in this expansion to determine the S0, the Eikonal, the CS1, which is the transport, and so let's go about doing that. So order 1 over epsilon, that's the biggest contribution. Here's what you get. Order 1 over epsilon, you get the dominant term from here plus a dominant term from there. And by the way, that's not supposed to, that's an epsilon, not an epsilon squared. That's my apologies. So that's an epsilon there. So you get epsilon here, and that's a 1 over epsilon squared. So this is a 1 over epsilon contribution. Then you get a 1 over epsilon contribution from here. And so that's what you get here. At next order, you collect. Here's what you get. Okay. So there you go, and you could keep going if you wanted, but let's just start solving these as we go. And let's say, what's the solution to the Eikonal equation? What's the solution to the transport? And so forth. So here is the leading order solution. This is the Eikonal equation. I get this equation here is equal to 0. Sorry, I forgot the 0. I'm doing awesome today. So this thing is equal to 0, so there's two possibilities. Either S naught x is equal to 0, or S naught x plus b of x is equal to 0. If S naught x is equal to 0, that's really easy to solve. It just means S naught's a constant. If S naught x is equal to minus b of x, I just integrate to get S naught. Okay, so two possible solutions. And remember, this is a second order differential equation, right? And so I'm expecting two solutions. And it's going to turn out these two solutions, right, are going to be, they're going to basically give us what we had before with our inner outer layers. Instead, I'm just going to get them as two linearly independent solutions. So let's start with the first case, the easiest case. S naught x is equal to 0. Okay, well then S naught's a constant. That's pretty trivial to solve. Then at the next order, if you use that, if for this branch of solutions, S1 is given by this solution here. So it's just an integral of the c over b. And then you can integrate that, put that in here, and you say, well, my solution then, u of x, is e to the S naught over epsilon plus S1. You can actually compute these things, and here is your solution. E to the minus 0 to x, b of c, c of c, d of c. So I can just, if you give me the specific b and c, I can integrate this. And it turns out this is actually, that's the outer solution we got before. It comes right out. So in other words, one of the branches of solutions that come from this, from solving this WKB, is exactly the outer solution we got before when we were doing boundary layer theory using our inner and outer expansions and in a matching region. Here, I just get the outer solution as one of the solutions. I can also go to the second case, which is S naught x is equal to negative b of x. And when I solve that, which is just, if you integrate that, the S naught's going to be the integral of b of x. I go to the next order. Here's the next order equation. And I can go and solve this. So now when you solve that, here is what the solution looks like. So actually, S1x is equal to this, right? If I rearrange a little bit. And then here is the solution. S1x is equal to, look at this integral, 0 to x, c over b, minus, now you get this extra contribution here, log of b of x. Okay? So we can go and plug this in, and here are the two solutions that we get out of this. So u of x is equal to, here's the solution form that we had, and one of the solutions, I'm just going to plug this in here. Here it is. This is one of the solutions. and here is, and now I can put them together. So this is the simplification of that second solution that had that extra term over here, which I want to keep around. Oh, actually, see, the 1 over b of x came from that log that I had in there. Okay? And then when I glue the two solutions together, here's what you get. Here's the solution that we first had with s naught equals 0. Here's the second solution. And what I've done here is just, I think I just rewrote this the same way as before. But now I have arbitrary constant C1. So this is the second solution that came from here, from this guy here. And I glue it together with the first solution, which was very easy to solve, which was our outer solution from before. So there you go. There's our two solutions. And this here basically is our outer solution. And that is something very similar to our inner solution. So it kind of basically reproduces for you what we got from boundary layer theory, except I didn't do any of the matching regions. I didn't do any intervariable expansions. It's all right there. Okay? And this is interesting, right? Because you have e to the 1 over epsilon. You see that 1 over epsilon there? This is my inner region contribution. That's my fast variable we had before where things were happening in the boundary layer. So that's the contribution you get automatically from WKB versus having to do a formal breakdown of an inner and outer region of an expansion. And first, of course, you have to know where the boundary layer is, do that expansion, and then match. Here it just gives it to you. Some final thoughts about this is that what about the validity of that WKB? Well, the WKB, right, is just this formal expansion like this. And, you know, this is going to be an obvious comment, I hope. But, like, basically what you're relying on is when these WKB approximations are used, you're really relying on this hierarchy that, in fact, delta S1 is less than S0, and delta S2 is less than S1, and so forth. So in other words, every term that you add to this gets smaller and smaller and smaller. So, right? So when you do this expansion, the whole idea of perturbation theory is that the next order terms should be a small correction to the previous terms. And that's exactly this hierarchy here of asymptotic orderings. The WKB holds provided that happens, right? Provided every correction term you add is a small contribution to what you already have. So that's the idea behind WKB. And you see what it is, right? It's just a different way to represent the solution. In fact, it's a constrained way to represent the solution as an amplitude and a phase. So you just plug that in. You solve for your Eikonal and transport equations and even corrections above that in a perturbation expansion. You're still using regular perturbation theory, but now it's constrained to this e to the s of x over epsilon form. And you expand the s of x. And of course, it doesn't have to be over epsilon. It could be over some delta, and you'd have to find that distinguishing limit first before you do the expansion. And so that's the idea of WKB theory, a very powerful technique commonly used in electrodynamics and quantum mechanics. Anything where there's very high frequency oscillations, WKB theory tends to play a big role in making approximations when you have these scale separations of some fast oscillation and a slow envelope on top of that. And this is the technique to go with when you have that.